is the maximum because that is the maximum area that we can consider. Remember, I wrote this statement, right? At point C, right? At point C, Q at point C is at its what? Q max. There's no other way that the area can get any bigger.
Right, thank you.
Does that right? It cannot get any bigger than that because that is where the centroid is. Good questions. Okay, now the next one I'm going to do, right? So over here, we happen to able to identify when to use a Bob's beam and when to use a wide flange. Okay, the difference is whether is it Q, is it 2Q, or is it Q? Okay, that's the critical part. So the next thing I'm going to teach now is I'm going to mix thin wall and thick wall. Okay, I'm going to mix thin wall and thick, and it's one of those questions even students at the graduate level have difficulty. Okay, and it's not difficult at all if you apply the rules. Okay, once you got the rules straightened up, you should be fine. As I said, this is one of the toughest topic in structural analysis. Okay, if you don't comply to rules. Okay, so the next example we're going to work this. Right, so we're going to look at example number 2. So our emphasis over here, the what you learn is analysis or combined analysis of thick wall and thin wall. Okay, so combine thick and thin wall analysis. So we're going to start from there. Okay, so I'm going to get the image again. So a very similar problem set that you see down here. So we are given that Vmax. Okay, we are given that Vmax. No, Vmax. What do I mean by Vmax? Tau max is equal to 75 times 10 to the power 6 Pascal. We're given it. Okay. So determine the shear stresses at the 3 points indicated. Okay. So again, a very similar format. They're giving you tau max because they want you to relate V over I, which is constant for everyone. And as long as you have your Q max over here and you divide by T. Okay. So for now, can someone want to make a guess? Okay. Can anyone want to make a guess? Where is tau max? Oh, sorry. I have to be careful down here. I have to careful. I will not put Q max over here for now, right? Because now there's a combination of thick wall and what? And thin wall. So we have to be really, really cautious over here. So now, can anyone tell me where is the maximum? Where is the location of the maximum maximum shearing stress? Anyone? Remember, let me remind you again. There is a combination of thin wall and thick wall. Anyone? Anyone want to make a guess?
At C.
At C. Okay. Anyone else? Why you say at C?
It's the thinnest and it's got the largest distance from the center.
Right. So yeah, right is the furthest distance from the center. Or can it be point B? You have bigger area. Yes or no? Right? You have a bigger. So you have to check. What I'm trying to say is check. And is it possible at point A? We don't know. Okay. We have to check. So for this case, okay, we have to check the location of the maximum shearing stress. I have not a clue where it is. Okay. So again, remember what I told you, right? So I'm going to copy this diagram. Right. So we know, right? We all know that the centroid is over here. We all know. We are aware that the centroid is here. That everyone knows. Okay, the green line over here. Right. So this is the position of our centroid. Then I'm going to shade. I hope this works. Right. This region that I'm shading, right? This region I'm shading is going to be for thin wall analysis. And then this region that I'm shading, you cannot classify this as thin wall, right? This over here is your thick wall analysis. Hey, I don't need a thick pen. Right? So we still have to what? We still have to do our shear flow. So you look at our shear flow now. So our shear flow will start from here. It will go from here, go here, and come down. And then over this side, it will go from here. Now, question for you. The top part, where's thin wall, is it a box beam or wide flange?
Wide flange.
There you go. Well done. Okay, it's wide flange, right? Because you see the initiation point is from two separate points. Are we clear? Right? We did not initiate from the what? From the same point. It's initiated from two separate points. That's why you say it is a what? It is a wide flange. Okay? Okay. So we're going to consider at point C. Get a shape point C. Right? So the shape point C is thin wall, wide flange analysis, where we only have what? Q, yes or no? And then the area to consider, right? We only need to consider this area now. Okay, we only need to consider this area now, right? We only need to consider that area. So the Q at point C, the width is equal to 50 minus 20. The thickness is 10. And the depth, the Y bar, okay, let me write down the formula. I do apologize. So this is width, depth, Y bar, and the Y bar is 160 divided by 2 minus by 10 divided by 2. Okay. On another note, it's a good practice when you say the thickness over here is equal to 10 millimeters. Right, so you will not get lost. So over here will be equal to 80 minus 5 times 10 times by 30 will be 22.5 times 10 to the power 3, and this is millimeter cube, or it's equal to 22.5 times 10 to the power minus 6 meter cube. Okay, so from here we can work out that the shear at point C is equal to V over Q V over Q. What am I doing now? V over I. And then the Q is 22.5 times 10 to the power minus 6. And then the thickness is what? 10 times 10 to the power minus 3. Okay, so over here, you get 22.5 power minus 6 divided by 10 power minus 3. You get 2.25 times 10 to the power minus 3 V over I. Yeah, I'll do it again. 22.5 power minus 6 divided by 10 power minus 3 is 2.25. Okay, so that is your shear stress at point C. And then you look at your shear stress at point B. Again, it's a thin wall analysis. Right? So thin wall analysis or thin wall wide flange analysis. Now you only have one Q, and the thickness now changed to what? Changed to 20 millimeters, right? So 20 times 10 to the power minus 3 meters. Okay, becomes 20 meters. So the Q at point B is equal to the Q at point A, right? Plus by width multiplied by depth multiplied by y bar. Okay. So from here, our width, the Q at point A is 22.5 times 10 to the power 3.
It should be point C.
Eh? Oh yeah, you're right. Q at point C, thank you. Plus by the width that is equal to 20 millimeters. The depth is 50 millimeters. The y bar is equal to 160 divided by 2 minus by 50 divided by 2. Okay, so you have to be really careful down here. Right, to get it wrong, this is where you get it wrong. Okay, so this will be equal to 22.5 times 10 to the power 3 plus by 80 minus 25 times 50 times 20 is equal to 55 times 10 to the power 3. So this is equal to 72.5, sorry, 77.5 times 10 to the power 3 millimeters to the power 3, or 77.5 times 10 to the power minus 6 meter cube. Okay, so over here you have to have the shear at point B is equal to Vn over I. So V over I is constant regardless whether is it thick wall and thin wall or thin wall. So now you have 77.5 times 10 to the power minus 6 divided by the thickness, which is equal to 0.02. And then you only need to do a 1 down here because it's what? Wide flange. Okay, so likewise, I did not put down here. You need to do a 1 down here because it's wide flange. Okay. So from here, you get 77.5 power minus 6 divided by 0.02 divided by 1. You get 3.875, right? So 3.875. So V over I, 3.875. Times 10 to the power minus 3 V over I. Okay, so let me check. So 77.5 power minus 6 divided by 0.02 divided by 1. Okay, so the last point that we are going to consider now, right? So the last point, let me copy and paste. Right. So the last region that we're consider is at point A. So when you look at point A, right, point A is not thin wall anymore, right? So it's going to be based on thick wall. Hey, it's going to be based on thick wall analysis. Now for thick wall analysis, we don't